This video is over simplifying radicals. So first we need to talk about parts of a radical. So right now we have the cube root of 144. So we need to know that this number right here is known as the index number or the index. So I'm just going to say index number, abbreviate number. Okay, the number on the inside is known as the radicand. So this number right here, 144, is known as the radicand. And then the whole entire thing is known as a radical. Okay, so those are the parts. I will be using the word index number and radical a lot throughout this video. So I kind of wanted you to know what I was talking about. And then another important tip is if the index number is not written, so an example would be this, it is automatically assumed that it is 2, which means square root. Okay, we just don't like to write a 2 there because that looks goofy. So we often just write it like this. So this and this are the same exact thing. Okay, so let's go on to some examples because that's the best way to show you. So we have two radicals being multiplied by each other. Before we can multiply them, because you cannot multiply radicals yet, we haven't learned how to yet, with different index numbers, we need to simplify them. I like to use the factor tree method just because it's more visually nice for people to see and they can understand the grouping and everything. So I like to break down the numbers. When you break down numbers using the factor tree, you want to use prime numbers. Prime numbers are only divisible by 1 in itself. It cannot have any other things that multiply to get it. So some prime numbers are, let's list a few of them out. Prime numbers. So we have 2, 3, 5, 7, 11, 13, and then they just keep going. There's more prime numbers than what I listed out, but if we look at all of these numbers, they only have 2 factors, 1 in itself. So there you go. Those are the numbers I'm going to be looking at. I like to start with the smallest prime number, but it really doesn't matter what you start with. So 27. I'm going to break it down. 2 does not go into 27, but 3 does. So I break it down to 3 times 9, and then 9 breaks down to 3 times 3. Once you get to a prime number, it's a dead end, and you just keep expanding the other side. Now, how we simplify this is you look at your index number, and that's how many things you need to be in a group for it to be able to leave the radical. So I have exactly 3 3s, which means a 3 gets to come out. They all join into one big 3 and they get to leave the radical together. Okay, when it's variables, you can always draw out a picture. You write out a times a times a. Again, I need a group of 3, so one big A gets to leave that group. So the cube root of 27a cubed is 3a. Now, looking at our second one, it's the 4th root of 32, b to the 9th power. We have to break down 2, so 32 breaks down to 2 times 16, 2 times 8, 2 times 4, and 2 times 2. Okay, for this one, our index number is a 4, so now we need a group of 4 like numbers. So I have 1, 2, 3, 4, and then I have a loner. Okay, the group of 4 gets to come out as a big 2. The one that's by itself has to stay in the radical. So it stays inside the radical. Looking at my variables, I'm going to show you this, drawing it out. So there's 3, 6, 9. Okay, you're not going to want to draw these out every time. So I'm going to show you another method that we can do instead. But again, we need groups of 4. So there's 1, 2, 3, 4, like that. And then there's 4 there. So each group gets represented by a b, and b times b is b squared. And I have 1 b left over, so it stays inside. How I like to think about it is kind of like long division. Okay, you take your exponent, you divide it by your index number. And you think, how many times does 4 go into 9 evenly? It goes in exactly 2 times, which gives us 8, with a remainder of 1. Okay, the 2 was the exponent of what came on the outside. The remainder is what stayed on the inside. It remained in the radical. From here, we simplified both radicals. Now we are able to multiply. So we just multiply the things on the outside together. So we have 3 times 2, which is 6. A times b squared, they're not the same base, so we can't add exponents. And then you attach the radical at the end. And this would be our final answer. Done. Moving on to another example. I have the 4th root of 81x squared y to the 5th power. So I'm going to break down 81. I'm going to do this one off to the side. So 81, 2 does not go into it, but 3 does. 3 times 27, 3 times 9, 3 times 3. We are looking for groups of 4. So I have 1, 2, 3, 4. So this is a perfect 4. So the 4th root of 81 is 3. Now I look at my variables. If I notice, I have this. 4 does not go into 2 evenly, so it does not get to leave the radical. Don't forget your index number. Okay, when I go to y to the 5th, again, I take my exponent of 5, I divide it by 4. 4 goes into 5 one time evenly. It has a remainder of 1, so a big Y gets to leave, and there is one remainder Y that had to stay in. And this would be simplified. Okay, moving on to the next example. We have 2 times the square root of 32x squared y. Again, there is no number written right here in the index number. We assume it's a 2 because that's just how it is. This 2 on the outside is being multiplied, so it's just going to follow along until the very end, and then we multiply by 2. So let's break down 32. 2 times 16, 2 times 8, 2 times 4, 2 times 2. I need it to be in groups of 2. So I have one group of 2, 2 groups of 2. For each group of 2, a big 2 gets to leave. So I have a group of 2, one big 2, and a second group of 2. And then I can't forget that I have this original 2 hanging out here. Okay? And then I have this 2 right here. It didn't have enough to leave, so it stays in the radical. Okay? I'm looking at my variables now. I have x squared. So 2 divided by 2 goes into 2 exactly one time. And I have no remainder, so I just have an x on the outside. The y is to the first power. There's not even enough to leave, so I'm not going to do the math for that. I just hope you know that 1 cannot be a group of 2. So it stays inside. And then we just multiply. 2 times 2 is 4, times 2 is 8. So I get 8x, the square root of 2y. And that would be it. Moving on to our next example. We have -3 times the 4th root of 62,208. X to the 12th, y to the 11th. So this is going to be a fun one to break down. So 62,208 breaks down by 2 to 31,104. Breaks down by 2 again to 15,552. By 2 again to 7,776. By 2 again to 3,888. By 2 again to 1,944. By 2 again to 972. By 2 again, which is 486. We go by 2 again. We keep going until we can't go anymore. To 243. When I get to 243, I see we cannot use the number 2 again. So let's switch numbers. Let's go to 3. Does 3 go into it? Yes, it does. So we have 3 times 81, 3 times 27, 3 times 9, and 3 times 3. And this is completely broken down. Yes, it was fun and it took forever. I'm going to change colors to group them just so we can see it better. We need them to be groups of 4. 4 of the exact same number. You cannot mix 3's and 2's together. Okay, so I have 1, 2, 3, 4. There's a group, so a 2 gets to leave for that group. 1, 2, 3, 4. There's another 2. Another 2 gets to leave for that second group. On to 3's. 1, 2, 3, 4. A 3 gets to leave. And then I have this 3 right here that didn't have enough to leave, so it has to stay on the inside. I cannot forget this original -3 on the outside. Now I'm going to go to my variables. Again, I take my exponent. I divide it by my index number. 4 goes into 12 3 times evenly, which gives me 12 and no remainder. So I get an x cubed to leave. When we go to 11, 4 goes into 11 2 times evenly, which is 8. I have a remainder of 3, so I get a y squared that gets to leave, but y cubed has to stay in. So my final answer, I need to multiply all these numbers together to clean it up some. So -3 times 2 is a -6 times 2 is a -12 times 3 is a -36. And then we have x cubed, y squared, and then the fourth root, don't forget your index number, of 3y cubed. This would be my final answer. Looking at our last example, we have the fifth root of 3,125. One thing you do need to understand is if it is an odd index number, odd, 3, 5, 7, 9 index number, you can have negative numbers under the radical without getting i's. That's that imaginary unit we talked about. Whenever we do this, whenever we factor it out or factor tree, the answer will end up being negative, and I will show you why once we get the answer. So we need to break down 3,125. 2 does not go into it, 3 does not go into it, but 5 does, and it becomes 625. We divide by 5 again. We get 125. We divide by 5 again. We get 25, and we divide by 5 again, and we get 5. So I need a group of 5 to leave. 1, 2, 3, 4, 5 right here. That right there gives me a -5 as an answer. So why is our answer negative? Our answer is negative because, let's look at it, -5 times -5 times -5 times -5, 1, 2, 3, 4, one more, times -5. If I pair them up, this equals a +25. I pair this up, this gives me a +25 times, this has no pair. When I multiply 25 times 25, I get 625 times a -5. Again, a positive times a negative is always going to be negative, which gives me that -3,125. So that is why it works. So odd numbers always have that third wheel that's left out that will always turn the answer negative. This is all for simplifying radicals. I hope you enjoyed the video.